Hi, my name is Jennifer Wenner. I teach at the University of Wisconsin-Oshkosh. I teach mineralogy. And today I'm going to talk to you about the optical indicatrix. The optical indicatrix is an imaginary three-dimensional figure that shows the index of refraction and vibration direction for light passing through the mineral. And when we construct it, we make a three-dimensional shape that reflects the indices of refraction as the radii of an ellipsoid or a sphere or a triaxial ellipsoid. We're just going to talk about three of these shapes today. And I want you to remember that when light enters a mineral, particularly when we're talking about in thin section, it encounters a slice of the indicatrix. So depending on how the light enters the mineral, perpendicular to that slice, perpendicular to that direction is a slice. And the indices of refraction, or the lengths of the radii of that slice, determine the birefringence that we'll see in thin section. And we're going to talk about slicing those indicatrices today. The shape of the indicatrix is related to the crystal system. And I just want to remind you there are 6 crystal systems. And they are defined by the lengths of their axes, or the relationship of the lengths of the axes, and the relationship of the angles between those axes. And each one has a different relationship. Today, we are going, first of all, when we're talking about the indicatrix, we really only need to think about the axes. And if we look at that, there are 3 unique relationships that we see here. And today, we're just going to talk about tetragonal, hexagonal, and isometric minerals. And so I just want to remind you that when we look at the axial lengths of these particular crystal systems, in the isometric system, all axes are the same. And in the tetragonal and hexagonal minerals, there's one unique axis. Okay, so, the optical indicatrix is related to that relationship. And I'm going to just summarize that in the next couple slides. Isometric minerals are also what we call isotropic when we're talking about how light behaves. Light encounters the same environment or the same index of refraction, no matter how it enters the mineral. Okay, so in all directions. Hexagonal and tetragonal minerals are uniaxial, and light encounters different environments or different indices of refraction depending on how it enters the mineral and what slice of the indicatrix it sees or it encounters. Okay, so when we're talking about tetragonal and hexagonal minerals in the crystal system, they have one unique axis. They are also known as uniaxial. When we talk about the indicatrix, we have a uniaxial indicatrix in which they have one unique indicatrix axis called the extraordinary ray, sometimes also called the E ray or the epsilon ray. The non-unique axis is called the ordinary ray or the O ray, or sometimes the omega ray. If the epsilon ray is greater than the omega ray, the mineral is positive. If the epsilon ray is less than the omega ray, the mineral is negative. But here I have M&Ms, Whoppers, and Jelly Bellies. And we're gonna talk about how these are related to the indicatrix. So let's just remind ourselves, the isotropic indicatrix has all the same axes. So if we construct something like that, it's going to look something like this. All of the Tinker Toys are the same size. And if we connected all of these axes, we would get something that would be a sphere, like a ping pong ball, which I have here. So I want you to think about which of the candies here is similar to an isometric or isotropic indicatrix, like this. It's the Whoppers, right? So the Whoppers are spherical, generally. They're not perfect, but that's okay because nature's not perfect. The indicatrix will be perfectly spherical because it's imaginary. But if we slice through the center of a Whopper, what shape are we going to get? So slice is a two-dimensional shape, but if we slice through a Whopper, or bite through it if you feel like it, you can see that we get a circle, which means the indices of refraction in this particular slice are all the same. Okay, so the light sees the same indices of refraction in all directions. It just sees n. Okay, it doesn't matter how we bite through, as long as we bite through the middle, which the slice is going to always go through the middle, we will always encounter a circle when we slice it. Okay, so that's the Whopper. Now, we also talked about uniaxial minerals, and uniaxial minerals have one unique axis, and all the rest of and perpendicular to that, they're the same. Okay, so the shapes that we get are what are called an ellipsoid. If the mineral is positive, the unique axis is longer than the ordinary axis. So light vibrates perpendicular to one another, so we get something that looks like this. This is a positive uniaxial mineral. It has one long axis and two short axes perpendicular to that. And it would look something like this egg if we connected it up, right? So here's our egg, looks something like that, okay? If we have a uniaxial negative mineral, we will have the unique axis, in this case it's yellow, smaller than the ordinary axes. And you get something that looks kind of like this. This isn't the best because it's not very circular, but something sort of a flat circular shape, okay? So if we think about these two shapes, and we've got two different candies, the Jelly Bellies are like a positive uniaxial indicatrix, one long axis and two short axes. M&Ms are the negative uniaxial indicatrix. So here we have those two uniaxial indicatrices. Okay. Now candy, who doesn't want to bite into candy? So we're gonna look at these two types of candy. I'm going to start with the uniaxial positive Jelly Belly. There's a long axis, and what shape are we going to get if we bite perpendicular to the long axis? So if we stick the long axis in our mouth, that's the way the light's traveling, and we bite through it, we get a circle. Okay? We get a circle, which is exactly like our isometric mineral or isotropic mineral when we bite through it. Okay? So it's a circle if we bite perpendicular to the unique axis. What happens if we bite parallel to the unique axis? Let's take another Jelly Belly and we'll bite parallel to it. That's not a very good one because I cut one. That's what it looks like, right? It has the maximum difference in axes. The long axis and the longest axis and the shortest axis. You get a large ellipse. What if we bite at some random angle? We get a smaller ellipse with a smaller difference in the axes of that ellipse. Okay, so here's a smaller one. It's hard to see, but imagine if you bit at some random angle. See how I cut it? At a random angle there. Okay. So you can see that the axis of the ellipse changes depending on the orientation of the slice. You can do the same thing with the uniaxial negative mineral. If we bite perpendicular to the unique axis, we get a circle. There's the M&M, it's very circular. If we bite perpendicular or parallel to, if we bite parallel to the unique axis, we get a large ellipse, the largest ellipse you can get. Okay, the axes are the most different. And if we bite at some random angle, we're going to get an intermediate ellipse somewhere between the largest one we can have and a circle. Now that we've talked about the different slices that you can see or that light can encounter when moving through isotropic and uniaxial minerals, let's talk about what that means about what we see in thin section. Remember that birefringence is calculated by subtracting the index of the slow ray minus the index of the fast ray. And the interference color that you see in cross-polarized light in the microscope is related to birefringence. Now, we know that isometric minerals and isotropic minerals, light sees the same environment in all directions. And that means there's no difference in interference or in index of refraction, and birefringence is 0. So if we find a mineral like this in plane polarized light and we cross the polars and it becomes extinct, the birefringence is 0, we have an isotropic mineral. In a uniaxial mineral, light encounters different environments depending on how it enters the mineral, and birefringence can actually vary in uniaxial minerals. We'll talk about biaxial minerals, which are the other kinds of crystal systems, in another video. So if we slice the indicatrix perpendicular to the unique axis or the e-axis in a uniaxial mineral, the shape we get is a circle, which means that all of the indices of refraction are the same in all directions, and that means that the birefringence is 0. Light behaves as though the mineral is isotropic, and we will see extinction. Okay, a slice parallel to the unique axis, meaning light is traveling from right to left in this image, it will see the O ray and the E ray. And you will see the principal section. So it sees the O ray and the E ray, and that means that you will see the maximum possible difference, and that gives you maximum birefringence. Okay, so that's the maximum you can see. That maximum is different for every mineral, and you can look up what the maximum birefringence is. Finally, if you have a slice that's random between E and O, so between E and O, there are infinite number of lengths between E and O, the slice will have an axis that is intermediate between E and O. And so it has E prime or epsilon prime, and O always has O. And so you will get somewhere between 0 and maximum birefringence, and you'll see some sort of intermediate birefringence, something between what could be maximum and 0. Okay, so as an example, here's quartz, there's the jelly bellies. If we just took this and sliced it through exactly as those jelly bellies are randomly oriented, we might see something like what we see in this quartz thin section, where we have blacks and grays, which have very low birefringence, which means they are lower than, they're close to the circular section where the light is very close, seeing very similar indices of refraction. And if we see something that is white or yellow, which is the maximum birefringence, then it's closer to the principal section. So that's the way that we can relate the indicatrix to the slice and then to what we see in thin section.